right, let's bring them in. All right, good afternoon, everybody. Happy fall Thursday, etc. Nice out there. Welcome back to your favorite class. Oh, I gotta say that. You can ingrain that in your head. Maybe you'll think it's true. Okay. Welcome back to your favorite class. Couple of announcements. First, your manufacturing breath assignment is due right now. I hope you got it in. Hope you learned some stuff. I mean, I think it's kind of an interesting assignment, like looking at composite manufacturing. Personally, I think it's a cool topic. I may be a little biased because, like, I'm kind of the professor for the course. I got my PhD in composites, so I'm a little biased, but, you know, what are you going to do? Right. So that assignment is due right now. That means that we have to dole out assignments for the manufacturing breadth document, which is the next, or not the breadth, the depth document, which is sort of your next manufacturing assignment. And if you go to Blackboard, you'll find a couple of new documents there. Okay, so I'm going to pull up my Blackboard right now and sort of show you what I mean. So if you go to Blackboard here, not the midterm, but the manufacturing report documents, you'll see that I've uploaded a variety of new materials, including the assignments for the manufacturing depth topic, as well as all these prompts for the different topics. And you can see there are a variety of different topics here. Sorry, I should be sharing my screen. Okay. So the depth topic assignments, as well as all of the documents going along with it. So you see there's a variety of different prompts here for all these different, manufacturing techniques. Autoclave processing, here we have carbon fiber, filament winding, glass fiber, etc. Okay. So to figure out which depth assignment you have to do, you want to click on this manufacturing depth topic assignments, and you find your name on this particular column, find your number, and see what number that refers to. Okay, so for instance, Preston Smith, front row in center here today. We scroll down the list here, Preston Lee Smith. I hope you don't want people to know your middle name, but now they know. You're number 8, Preston Lee Smith, and that means that you have to write a depth document on 8 resin transfer molding. Boo, he says, boo. I was saying boo earns. Okay, it's a Simpsons quote for anybody. Okay, so we come over here, we look at the resin transfer molding. You can click on this and download it and open it. And Preston gets to read all about what he has to write about. Which here, I've tried to give as much like detail about what I want for this particular assignment as I can. But here, Preston, you need a detailed overview of the processing technique, all this stuff, yada, yada, yada. You got to make a figure about what the process looks like, and you must make this figure yourself. Rawr! Okay? Must make it yourself. Okay. List of commonly manufactured items, and then a variety of different information. I ask you to get a quote for an RTM machine. If you can do that, mad props. Okay? So all the different sort of props for the depth documents look a little bit like this with slight variation. So find your topic, get thee to your prompt, and then write me a 3 to 5 page document on this particular process, or carbon fiber, glass fiber, etc., whatever it may be. And it's going to be due Tuesday, November 3rd. So that is like 1 month from now, 4 weeks from now. Okay? Got it? Got it? Got it? Got it? Got it? Okay. What's that? Yeah, got it, got it, got it, got it. Once forever, all 28 of you inside that, that online world. Okay, so that is going to be due the 3rd of November. Remember the 3rd of November. Okay. Next, your first exam for the class is due, or is not due. It's going to take place next Thursday. I've also uploaded to Blackboard instructions for how that exam is going to go. So if you go to the exams tab, go to the midterm exam. You can also find your exam instructions here now. So I have a nice little picture of how I want you to set this up, and with yours truly in the image. So the idea is you mute your microphone, you turn your camera on, you point it towards your workspace as best you can, and I will release the exam right at 4 o'clock, and you execute, okay? You don't have to copy the problem statement down. You don't have to, do any of that. Just like write number 1 and go to town, okay? Number 2, do the thing. Okay. So there you go for the exam. After 50 minutes are up, take a picture of it, scan it in, whatever, and send it to me. As long as I receive it by 5 o'clock, you'll get credit. 5:01, SOL. All right. So take a look at that. All right. I had a question in the chat from Xavier. Xavier says, so for the anisotropic materials, are we going to be expected to work out those matrices in the test? I don't exactly know what you mean by that, but you're gonna be responsible for material through slide 8 of this current lecture that we're on, lecture 6. So information regarding, transforming stresses and strains, that's something I might expect you to do. Like T. Yeah, I'm not going to ask you to calculate a full T matrix for the test. That's ridiculous. Okay, that would be insane. I'm not that mean. Okay, like I am kind of mean, but not that mean. All right. Okay, woo. He says he's wooing. He's a woo guy. For those of you, How I Met Your Mother. He's a woo guy. Okay. Other questions? More of a few guy. Okay. All right. Well then, as they say in Mulan, let's get down to business. I thought it was crazy that, Disney made Mulan, like the live action Mulan, and they released it on Disney Plus. So you have to have a subscription, and then you also have to pay $20 on top of that to watch the movie. Ah, did anybody even watch that? Like they released it with all this hubbub. I don't even think anybody watched it. Oh, was it bad? Okay. They took out Eddie Murphy, who's the dragon. Come on. All right. Well, let's get down to business to defeat the Huns. All right, let's talk about where we had left off. Last time we left off, we were talking about transformations and specifically about transforming stresses and strains from one coordinate system to another, and also transforming stiffness and compliance matrices from one coordinate system to another. So just to sort of remind yourself, if you have one general coordinate system here, that's like the 1, 2, 3 coordinate system, and you have another coordinate system that is aligned somehow differently than that, X, Y, Z, let's say, then you can transform your stresses, your strains, your stiffness matrix, your compliance matrix, etc., to that alternate coordinate system or back using a variety of different transformations. All right. So one way that you might do that is sort of transforming stresses. You might have something like the stress in the 1, 2, 3 coordinate system is equal to this transformation matrix that we sort of showed before. I'm not going to write the whole thing. It's a 6 by 6 matrix multiplied by stress that exists in X, Y, Z. You could also imagine the inverse of that, or if you want the stress in the XYZ coordinate system, you multiply T inverse by sigma 1, 2, 3. Well, that's pretty straightforward. We also looked at strain. So reminder, this is a 6 by 1. This is a 6 by 6. This is a 6 by 1. The strain, also similar idea. Here, 1, 2, 3. If you want the strain in the 1, 2, 3 coordinate system. Here we have a sort of modified transformation matrix we call T star, and it's because of that wonky factor of 2 that sort of floats around there, and we sort of define the strains. Multiplied by strain X, Y, Z. So that was sort of transforming the stresses and strains, but we also may consider transforming stiffness and compliance matrices in each one of these coordinate systems to another coordinate system. And just to remind you, sorry, I'll bring this back up. Your Hooke's law, and I'll say Hooke's laws because we kind of have both directions. That is that the stress in any arbitrary coordinate system, let's say the 1, 2, 3 coordinate system, is this stiffness matrix C, and here we'll specifically say the 1, 2, 3 coordinate system, multiplied by the strain in the 1, 2, 3 coordinate system. Hold on just a second. Can I help you? Yeah, I'm in the middle of lecture. Yeah. Okay. Sorry, some janitor just walked in and was asking about something. Okay. So here we have Hooke's law, stress in terms of the strains. We could also go the other direction, strain. 1, 2, 3. Written in terms of the compliance matrix, 1, 2, 3, multiplied by the stresses, 2, 3. Let's say that's in the 1, 2, 3 coordinate system. And here, reminder that this is the stiffness matrix. It's also a 6 by 6. And this capital S, obviously, compliance matrix, which is a 6 by 6. And we'll also note that C and S are inversions of each other. It's pretty obvious from these sets of equations that that is true, but we can sort of explicitly state this here, just so we all know that. And the other way is true. The inverse of C is S. Okay, so these are all kind of the math precursors that we had been working our way through. So as I sort of mentioned, not only do we have these compliance and stiffness matrices C and S in the 1, 2, 3 coordinate systems, but we could also rotate them to the XYZ coordinate systems or vice versa. So we can also transform S and C with T and T star. And we sort of derived that last time. And we saw that those were like, if I want the compliance matrix in, let's say, the X, Y, Z coordinate system, then I want T inverse times compliance matrix 1, 2, 3 times T star. If I want the compliance matrix in 1, 2, 3, given a compliance matrix in X, Y, Z, then I want T times C, X, Y, Z times T star inverse. I can go through the same sort of process for the compliance matrices. So if I want the compliance matrix in the X, Y, Z coordinate system, I can use T star inverse multiplied by the compliance matrix in 1, 2, 3, multiplied by my transformation matrix T. And finally, if I want the compliance matrix in 1, 2, 3, I can do T star times S, X, Y, Z times T inverse. And these are all the relationships that I can have, transforming stresses and strains in between coordinate systems, relating stresses to strains to each other with stiffness and compliance matrices, and also transforming stiffness and compliance matrices. God damn, that's a lot of math. Okay, but now the cool thing is, after all that math is out of the way, we're ready to start talking actually about composites. Okay, all right, finally, what you've all been waiting for. And that's where we sort of pick up the lecture now. And what I would say is like a new set of lecture notes. Okay. So let's now talk about composites, and let's consider a unidirectional composite for a second and how we might construct a stiffness or a compliance matrix for a unidirectional composite. Okay, so let's now consider the 1, 2 plane of a unidirectional composite. Okay, the picture you should sort of have in your head for a 1, 2 plane is this guy here, where all of your fibers, like normal, are sort of running in the one direction. Oh, I forgot to put my soundtrack on in the lecture lobby for my One Direction. Dang it. Next time. All right. We've talked about planes of symmetry and planes of isotropy. It's pretty easy to see here. This is a plane of symmetry. A 180-degree rotation about the 3-axis, which is kind of coming out of the plane here, would leave the stiffness properties of this guy unchanged. Okay. So this is a plane of symmetry. Remember, we had a definition for plane of symmetry. That means a 180-degree rotation about the 3-axis leaves properties unchanged. Okay. So let's say that we do this. Okay. I want to look at what is the stiffness matrix of this particular composite right here versus what is the stiffness matrix of a composite that is rotated 180 degrees from this current configuration. We know those two things are the same, but let's apply our mathematical concepts, our transformations to that, and sort of see what happens. Okay. So what I want to do is I want to rotate 180 degrees about the 3-axis into a new coordinate system that I'll call the 1', 2' coordinate system. So this is my rotation angle theta, it's 180 degrees. Okay, so rotate from 1, 2, 3 to, I'll say 1', 2', 3', even though we know 3 and 3' are the same. Okay. Since plane of symmetry, we know the following to be true mathematically. The stiffness matrix in 1, 2, 3 is going to be equal to the stiffness matrix after our rotation, 1', 2', 3', because this is a plane of symmetry. And that just like makes sense when you look at this picture. Okay, if I just take this 1, 2 plane and I rotate it 180 degrees, it's going to behave the same way as it originally did, right? It's pretty easy to see that and understand that, I hope. So let's apply now the math that we've sort of talked about to this idea, all right? We're going to make this assumption that it's the same in the 1, 2, 3 and 1', 2', 3' coordinate system, but now let's apply our math to this. And so we can write the following, that the compliance matrix in 1', 2', 3', after using our transformations is something like the transformation matrix T for a rotation of theta 3 is 180 degrees, multiplied by my original stiffness matrix C in 1, 2, 3, multiplied by my T star matrix for theta 3 equals 180 degrees, inverted. Okay, hopefully we're all sort of understanding this general idea. I'm starting with this guy, and I want to know what it looks like in this coordinate system through those transformations that I just described like at the beginning of this lecture. Okay, so remember this is 6 by 6, this is 6 by 6, this is 6 by 6, this is 6 by 6. Everybody's a 6 by 6. You get a car, you get a car. Okay. I'm Oprah. I'm the Oprah of giving out 6 by 6 matrices. Okay. Well, remember this T matrix, this transformation matrix was given by that crazy equation that I didn't actually write in lecture, but is available in your notes. Okay, so if we kind of go back, I'll pull that up here quickly so we just sort of see and remember what it looks like. It was this matrix here. Please don't write this down. Okay, but the idea here was that we could, given some angles, you know, theta x1, theta x2, etc. You know, we could define all these directional cosines, m1, m2, m3, etc., given our 180-degree rotation. And this is something you might do on your next homework. Okay. Maybe. Okay. So the point is you could populate that Tij matrix. And I will just tell you that that Tij matrix, let's see if I can get rid of this. Go away. Okay? I'll just tell you that the Tij matrix is going to be this. So here, this T matrix, if you plug in all the values appropriately, is going to look something like this. 1, 1, 1, -1, -1, 1 in the diagonal, and zeros everywhere else. Okay. This is for theta 3 equals degrees. Interestingly, we would get the same thing in the T star matrix. Also the same. Okay. Give you one more second here. These are all zeros, by the way. All zeros. On the right-hand side, you would end up with. Why does this keep like erasing? Why does this keep going away? Hey. Why do they keep disappearing? My marker's running out of ink. Do I need to like move down more? Okay, that worked fine. What the heck? Okay. What? Okay, that was odd. On the right-hand side here, you'd end up with a matrix of your stiffness constants that looked like the following. I'm going to have to write this out fully, okay? So if you started with this full guy here, with entries like C11, C12, C13, C14, all the way through to C66, after transformation, you would have the following. Sorry, I forgot some negative signs here. Negatives are important. I'll highlight the negatives with red. How about that? That'll help. Or will I? Okay, I will. Keeping it going. Okay. Keeping it moving here. I know it's annoying. I'm only going to really do this once, so. And I didn't do a great job aligning it, so sorry about that. Why is it like selecting multiple things? Stop that. Stop it. No. All right, I think I'm gonna have to do the old engineering solution. Turn it off, turn it back on. I can't even do that. God. Okay. Okay. C5, 6. Ugh. Yikes. That was quite the ordeal, and I'm not even quite done yet. Ugh. Gross. All these negative signs. There's 16 of them. Is there? Oh, no. Okay. Now I got them all. All right. Sorry. Got them all now. I promise. All these negative signs come strictly from that 180-degree rotation. All right. It's just a mathematical phenomenon. All right. After this rotation, we have all these negative numbers here, right? But we know that this stiffness matrix here, this 6x6, has to be equal to our original stiffness matrix, right? Because we know by a plane of symmetry that the current configuration, the 0-degree orientation, has to be the same as the 180-degree orientation, okay? So this would be like after 180 degrees of rotation. This must be equal to the matrix here of basically all these entries as positive values. Okay, this is original. CI. Okay. And we say that they're equal because plane of symmetry. But we've applied our math to show that if we do this 180-degree rotation, we get all these negative signs that pop in. And this is just a mathematical phenomena that exists by doing this transformation from the 1, 2, 3 coordinate system to the 1 prime, 2 prime, 3 prime coordinate system. So for this generally to be true, what does it mean about these entries that pop up here that now have negative signs? They have to be 0. Thank you. Okay. In order for a negative entry to equal to a positive entry, that entry has to be 0. Okay. So therefore, math says, for instance, if negative C14, I'll pick on C14, is equal to positive C14, then C14 has to be equal to 0. Okay. And not only for this C14, but also all these other guys. C15, C24, C25, all the ones that I sort of put negatives on. C34, C35, C46, C56. Okay. If we have one plane of symmetry, we just eliminated 8 material constants that are required to define this thing. All right, useful. Okay, so then we know if a material has one plane of symmetry. We can write stiffness matrix in plane of symmetry as the following. Yeah? We have to remember that we're symmetric here. As something that looks like this. Oh, made a boo-boo here. Got to be symmetric. So we've simplified from this general stiffness matrix, which has 21 independent values, down to a stiffness matrix with only 13 independent values, just by sort of demonstrating that this 180-degree rotation, if it does leave the properties unchanged, would force all of these entries in the stiffness matrix to be 0. So here, we've gone from 21 constants for what is a general anisotropic material to 13 constants. A material with one plane of symmetry and only one plane of symmetry is known as a monoclinic material. Monoclinic materials have exactly one plane of material symmetry. Right? Monoclinic material is exactly one plane of symmetry. There are not many examples of materials like this that exist in the world, but there are some very rare gemstones that exhibit this behavior. You guys learn about like single crystal, you probably learned about this in your material science class, like rectangular unit cells, some materials with rectangular unit cells. No. Face center cubic, body center cubic, these like ringing bells. Okay, yeah. So there are like, yeah, now you guys are crying, exactly. An example, gemstones. Specifically, there's 2 of them here that I have in the notes, gypsum and jadeite, which I'm sure we all have at home, right? But okay. I'm gonna gyps someone off. Jadeite. So here's I took a picture from Wikipedia of gypsum, put it in the notes because I thought it was cool. Why did you go there? My cursor is here. Go there. Thank you. Okay. I think that's kind of cool. So this particular material only has one plane of material symmetry, and you would need 13 material constants to sort of define its behavior. Complicated. Yes, question. So the question is the unidirectional composite that I used to motivate this example a material with one plane of symmetry? And the answer is yes, it does have one plane of symmetry, but it also has other planes of symmetry that we know about. So if you wanted to think about classifying these materials, it has at least one plane of symmetry, so I guess it would be classified as monoclinic, but you can further classify it more specifically. Okay. All right. So the next we're going to talk about is an orthotropic material. I have a question. Is it Alex just complaining about his hand again? Wow, lots of I heard it bombed hard. They must be talking about Mulan. Shared composite Disney Plus account? Question mark. I do have Disney Plus account. How are you sharing it with you guys though? They tried to appeal to the Chinese market, but the Chinese consumers thought the movie was insulting. Yeah, I imagine that is probably true. Um, some people talking about my RAR. Okay, nothing useful. All right, so thank you for enjoying my RAR. Just a bunch of random stuff. RAR! Okay. Orthotropic materials. An orthotropic material, remember by definition, has three orthogonal planes of symmetry. Okay? So that means that, like, degree rotation about any of 1, 2, or 3 axis would leave props unchanged. Okay? So the idea here is that we would start basically with the monoclinic stiffness matrix, by thinking about rotating it about the 3-axis, right? We have that 13 constant stiffness matrix. We could do that one more time by, like, let's say, applying a 180-degree rotation about the 2-axis and enforcing that, what we had before and after is equal. And we could also do a 180-degree rotation about the 1-axis and enforce that it's the same before and after. And we would also have a lot of these zeros kind of like canceling out. So it would be the similar procedure, and you're actually going to do that procedure for your homework. Congratulations. Okay. So similar process. And you'll end up with a stiffness matrix that looks like C1, 1, C1, 2, C1, 3, 0, 0, 0. Oh man, might need a little more space here. I like when there's a lot of zeros. Makes the calculations easier. There you go. So here now we have what would be 1, 2, 3, 4, 5, 6, 7, 8, 9 independent constants. So we've gone from 21 to 9. We've gone to plaid. I have not complained, says Alex. And he put a Zen taco picture in the chat. Okay. It's not Taco Tuesday, it's Thursday. Taco Thursday? I guess it could be. All right, 9 independent constants here. All right, so we're whittling our way down. So an example of an orthotropic material would be a stacked unidirectional composite. So stacked unidirectional composites. We sometimes call this a laminate. And by sometimes I mean always. A picture that you're going to want to think about in your head for a laminate, and we'll get to this a little bit later in the course. We've talked a lot about unidirectional composites, but if you stack unidirectional composites on top of each other, you end up with a picture that looks something like this. This is a laminate. All right. So we see, for instance, like this guy on the top, he's got fibers running this way. The guy in the bottom, he's got fibers running this way. And this one has like 45 this way. This one has like 45 this way. So you can sort of see this is like stacked layers on top of each other. We would call this a composite laminate. You would need 9 independent elastic constants to define this particular piece. Continuing. The next most specific material we'll talk about is a transversely isotropic material. So a transversely isotropic material is one that has exactly one plane of isotropy. So remember that a plane of isotropy is different than a plane of symmetry. Remember, a plane of symmetry is a 180-degree rotation about an axis out of that plane leaves the property unchanged. A plane of isotropy is any rotation in the plane leaves the property unchanged. Okay, so slightly different. And so an example, remember, of a plane of isotropy is like the 2-3 plane of unidirectional composite. Okay, so remember your 2-3 plane of unidirectional composite would be like chopping through the fibers in the 2-3 plane, and you would see something like this. Okay, so the idea here is that no matter how we rotated this particular cross section, loaded it in any particular direction, you would have the same sort of behavior. Okay, so the rotation, I'll say any rotation, about the one axis leaves properties unchanged. here, we have the following stiffness matrix. Yes, that C12 is meant to be there twice. That is not an error. Same thing with that C22. Okay, that's because the 2 and the 3 directions are the same. So we would expect like the 2-2 and the 3-3 entries to also be the same. Hopefully that sort of makes sense. This one's a little bit strange, and I'll explain this in a little bit more detail, probably in a later lecture. The 4-4 entry is C22 minus C23 over 2. Sorry, it's kind of a sort of out of space there. Okay, strange one. Now we see we have 1, 2, 3, 4, 5 independent elastic constants. These 5 you should be familiar with, okay? And that's because we've done micromechanical models on unidirectional composites. We've had to calculate what is E1, what is E2, what is nu 1,2, what is G12. And even though we didn't do it, you could also calculate G23. Okay, so those are your 5 constants that you could use to fully define the stiffness matrix. They don't appear here as E1, E2, nu 1,2, etc., but you can write the entries in this particular stiffness matrix using those engineering constants that you know. We're working towards that right now, but I just generally want you to understand that there are 5 independent elastic constants here. Okay, so an example obviously is a unidirectional composite. Okay, lastly, this is the last one we'll talk about, obviously is an isotropic material. In this situation, all planes are planes of isotropy. And I'm kind of running out of time here, but you've sort of seen this already. Stiffness matrix is this is in your notes. I'm just going to copy this down sort of for speed reasons. Is here. And we have seen a form of this with actual engineering constants, which was this guy. And obviously examples of isotropic materials, I don't need to tell you what these are, hopefully. Aluminum, steel, you know, most polymers, just take your pick, you know, epoxy. All right. The last thing that I'll do, I'll leave you with the cliffhanger, leave you hanging on for the weekend, is how do we go from this form, which just has these general like C1, C2, etc. And we've seen this for all the sorts of types of symmetry we've talked about. How do we go from this to this, which is like engineering constants? And that's what we'll tackle the beginning of next week. Could I scroll up to the transversely isotropic section? We got a lot of people right near Riley. Sorry. Maybe just go revisit the YouTube page when this is over. And that's it for today. 1 minute late. Sorry about that. Too many Mulan jokes. Okay. Have a good weekend, guys.